Hi everyone, so I'm going to take you today through the 2018 AS Maths paper for mechanics, and if you were in my group you would have been doing this recently during lockdown as one of your exams. Okay, so let's get started, but it's always good to read this bit as a bit of a reminder at the beginning. Unless otherwise indicated, wherever a numerical value of g is required, take g equals 9.8 meters per second squared and give your answer to either 2 significant figures or 3 significant figures. So that's quite an important thing that we've got there. Okay, answer all questions, write your answer in the space provided. A man throws a tennis ball into the air so that at the instant when the ball leaves his hand, the ball is 2 meters above the ground and is moving vertically upwards with speed 9 meters per second. The motion of the ball is modelled as that of a particle moving freely under gravity, and the acceleration due to gravity is being modelled as constant magnitude 10 meters per second squared. Usually it's 9.8, isn't it? But in this case, they've asked you to use 10. The ball hits the ground t seconds after leaving the man's hand. Using the model, find the value of t. Okay, I always like to draw a quick sketch of this. So there's this man stood here, and I'm going to pretend it's almost like a cliff or a platform, and there is a ball, and it says that it is going to be projected upwards. And first of all, it says it's 2 meters above the ground, so I know that this distance here is 2 meters. It says that the ball is going to be projected upwards vertically with a speed 9, and then it's going to move freely under gravity. So it's going to go up in the air, and then it's going to come down, and it is going to hit the floor. So I might as well draw that we've got the floor in here as well. It's also told us that the acceleration due to gravity is 10 meters per second, so I'm going to put that on with my double arrow for the acceleration. And I've got 1, 2, 3 different values, and it wants me to find out how long it takes for it to hit the ground from leaving the man's hand. So this looks like I'm going to be doing some suvat. Okay, and I think I've got, if it's going from here to here, then looks like I'm going to go with downwards being positive, but you may have done a different way of it being positive. You may have done it upwards, but that shouldn't make a difference. Okay, so I'm just going to grab the values I know really easily. So first of all, the acceleration is downwards, so it's just going to be that the acceleration is 10. I can also see that the initial speed is 9, but it does look like it's being thrown in the negative direction, so it's going to be minus 9. Now I'm going to look at the displacement. Now this is where sometimes people get a bit confused, but the displacement is actually saying, imagine you took a photo of it at the beginning of this suvat journey and a photo at the end. All you would see is that it has moved here downwards 2 meters. We're not bothered about this part of the journey for suvat. Just from the beginning of the journey to the end of the journey, it has displaced downwards 2 meters. Downwards is positive, so I'm just going to go with 2. So I've now got my 3 values, and I want to find out what the time is for this to take. And they've said that my time is capital T. You'll notice with suvat, I don't write out S-U-V-A-T. I just write out the ones that I have and the one I need, because it makes this next step a bit easier to spot which equation I need. So I've got S, U, A, and T. That must mean that I've got, let's get rid of this, always asking me to install. And let's actually do it with our formula, S equals UT plus a half a t squared. And I'm just going to substitute everything in really carefully. So S is 2, and U is minus 9, and T is capital T, so that's minus 9t. And then I've got a half a, well, a half of 10 is 5, and then I have t squared. So you can see here that I've got a quadratic, so I'm just going to rearrange it to have it equaling 0. So that's 5t squared minus 9t minus 2. And then I'm going to be really lazy, and you should all be doing this too. I'm going to go to my calculator, I'll put my quadratic solver on, and I'm going to put it in with my coefficients of 5, minus 9, and minus 2. And the values that I get are that t equals 2 or minus 0.2. But clearly we can't have a negative time, so t has got to be greater than 0. So we're going to just say that t equals 2. Okay, so that's a really easy first question for suvat there. I'm just going to really quickly show you the mark scheme so you can see how you'd get those 4 marks. So first of all, just an equation that only has t in it, and if you get it, if it's an s equals ut s equals ut plus a half at squared, you get 2 marks for getting this bit here, because you've got the accuracy mark as well. The third method mark is actually just for solving the equation, but you can just solve this equation on the calculator. So the last mark is just for coming up with t equals 2. Nice, easy question there. Okay, question 7. A train travels along a straight horizontal track between two stations A and B. In a model of the motion, the train starts from rest at A and moves with constant acceleration of 0.3 meters per second squared for 80 seconds. The train then moves at a constant velocity before it moves with constant deceleration of 0.5 meters per second squared, coming to rest at B. So it's starting from rest at A, it's accelerating, it's then got constant speed, and then it's decelerating to rest at B. For this model, state the value of the constant velocity of the train. Well, you can either use a Suvat formula, or you can use a bit of common sense that you might have here. So if something is starting from 0, from rest, and it is accelerating at 0.3 meters per second for 80 seconds, that means every second it is getting 0.3 bigger. And it's doing that for 80 seconds. So if it's doing 80 seconds of increasing by 0.3, then you just do 80 times 0.3, which is 24 meters per second. Now, if you can't see that, instead, you could do a quick bit of Suvat. Say that it's starting from 0, it's going up to the thing that we're trying to find, what is v. The acceleration is 0.3, and the time is 80. So using v equals u plus at, very clearly you can see that v is equal to, well, that's 0, 0.3 times 80, which is the same thing that we've got here of 24. Okay, so part 2 of this question, it wants us to find out the time for which the train is decelerating. So we now know that it has gone up to 24 meters per second, and then it's going to be decelerating. So there's a few different ways you can do this. One, you can do the kind of common sense. You can say if it is at 24 meters per second, and every second it is decreasing by 0.5, we want to find out how many 0.5s there are in 24 for it to go all the way to 0. So we can think about doing 24 divided by 0.5, which gives us 48 seconds. If you can't see that kind of common sense approach of it, you can do some Suvat and say, well, the current speed that it's got when it's at this constant speed is 24. We've just worked that out. And we know that it's going to go all the way down to 0, and we know that it is decelerating at 0.5. So I'm going to have to put it as a minus 0.5 because it's a deceleration, and we want to find out how long that is going to take. So we know that v equals u plus at, so that's 0 equals 24 minus 0.5t. Rearranging this, 0.5t equals 24, so t equals 24 divided by 0.5, which gives you the same answer of 48 seconds. Now for part 3 of this question, it wants you to sketch a velocity time graph. I always think about sketching this first because it kind of makes, to me, it makes a bit more sense to visualize what's actually happening here. So we know for this velocity time graph that it is going to be accelerating up to 24 seconds, and it does that for 80 seconds. It then has a constant velocity, but it doesn't tell us how long it has a constant velocity for. And then it is going to decelerate a little bit quicker, so it's probably going to be a bit steeper down here. And we can't label what this bit on the axis is, but we do know that this section here, it takes 48 seconds for it to do this. Now to get that third mark, you actually only need the shape of the trapezium that you have there, but I've added on these bits because I think they're going to be useful in the next parts of the question. Part B of the question says that the total distance between the two stations is 4,800 meters. And actually all the units so far are in meters, so we don't need to do any conversions. If you think about this, let me see what the question says. Using the model, find the total time taken by the train to travel from A to B. Well, this is A at the beginning, and this is B where it comes to the next station. Now, if you remember, the area under the line, or area under the graph, is equal to the distance that is travelled. So we know that the area under the graph is going to be 4,800, and this shape that we've got here is a trapezium. You may do this as a triangle, a rectangle, and a triangle, but it is way better to do a trapezium, because if you have a more complicated question, this one's kind of simple, then a trapezium will make your algebra way easier to do. So quick reminder of the formula for a trapezium. It is a half a plus b h, which is a half of the average of the parallel sides multiplied by the height. So in this particular one that we've got here, the height is going to be 24. And we've got the half that's just going to stay there. Now, A and B are the top and bottom. We haven't actually labelled what this top is. We don't know how long it has constant velocity for, so I'm just going to call it t, which means that this bit along here is also t. And we know, because it takes 80 seconds for that beginning bit, that this bit here is 80. So I've got 80, t, and 48 for B, and for A, I have t. So I'm just going to set that up as an equation. So my area under the graph is a half. A is the top bit, which is going to be t, and B is the bottom bit, which is an 80, a t, and a 48. And that's all being multiplied by the height, which is 24, and that's equal to 4,800. Now you're welcome to expand this, but I think it's going to be easier to just deal with the half and the 24, which is just 12, and then the inside bit is 2t plus 128, and that's equal to 4,800. Now again, you could expand this, but I just think it's going to be quicker to divide both sides by 12. So we get 2t plus 128 equals 4,800 divided by 12, which is 400, just checking everything to be super careful on my calculator. And then I'm going to solve the equation for t by subtracting 128, and then I'm going to divide by 2. So we get that t is equal to 136. Let's actually see what the question was asking. Use the model, find the total time taken by the train to travel from A to B. Well, we've worked out that this section is 136, but that's not what it asked for. It didn't say how long does it have constant velocity. It wants to know the total time. So the total time is going to be 80, the beginning bit, plus 136 plus 48. Which is 264 seconds. Okay, let's have a look at part C. Suggest one improvement that could be made to the model of the motion of the train from A to B in order to make the model more realistic. Well, you may have seen this if you've looked at any of my other lessons before on these speed time graphs. The thing that is unrealistic is that you cannot go from a constant acceleration to a constant velocity instantly like that. There would usually be a smooth kind of changeover. There'd probably be a smooth bit at the beginning and a smooth bit over here. So we need to just express that in a sentence here. We should say something like, what did the question actually say? Let me remind myself. It's just one improvement that could be made to the model of the motion. The acceleration, let's say, the change between constant acceleration and constant velocity could be smoother, or we could say something like acceleration could be varied or be variable for the start of the journey. Let me remind myself, I'm never as good at these ones. Let's remind ourselves of what's been said in the mark scheme, just to see we can definitely give you the perfect phrasing for this. Okay, so we'll just double check our answers. So we've got 24 and 48 and the shape of the graph. And you get one method mark for trying to do the area being equal to 4,800 with just one variable. You get an answer mark for actually coming up with it correctly, and then a third answer mark for getting t equals 136 and 264. So we've got either a smooth change from acceleration to constant velocity, or from constant velocity to deceleration, or have the train accelerating or decelerating at a variable rate. Notice here you can't say anything about air resistance or resistive forces or the straightness of the track or anything. They only want to hear things about the smooth change from the acceleration. So we've said here the change between the constant acceleration and constant velocity could be smoother, or could be smooth, I suppose. So that's those ones we've got so far. So we've now had one on SUVAT, we've had one on speed time graphs. The next topic that we come up with in question 8 is variable acceleration. And we can tell that this is going to be variable acceleration because A, we haven't had it yet, and we've been told what x is in terms of t. So for question 8, let's have a look at part A. A particle P moves along the x-axis. At time t seconds, with t being greater than or equal to 0, the displacement x meters of P from the origin O is given by x equals a half t squared minus 2t plus 1. If I see this as someone who's been teaching for a long time, I would look at this and I'd think, there's something I can do to this. I'm not going to deal with it just yet, but just keep that in mind for later. It wants us to find the times when P is instantaneously at rest. It doesn't mean it's going to be at rest and it's stopped. It just means very briefly it's at rest. A bit like when you throw something in the air and at the peak of that journey, it is instantly at rest just for a very brief second. Now, if something is at rest, that doesn't mean that the distance is going to be equal to 0. If something is at rest, we know that v is equal to 0. And we've been given the displacement. So let's just remind ourselves. We know that we've been given the displacement s, and we know that we get s, u, v, a, t in terms of SUVAT. And if you want to go downwards to go to the next one, downwards means you differentiate. And if you want to go upwards, you must do the opposite, which is you integrate. So we've been given the displacement, and we want to find out something about the velocity, so we're going to differentiate it. So if we have that x is a half t squared minus 2t plus 1, I can't differentiate this yet, so I need to make sure that I first of all expand the brackets. So I get a half t to the power of 4 minus, well, a half times 2 is just 1, so it's minus t cubed plus a half t squared. Now if I differentiate this, I can say dx dt is equal to v, or I can just say what v is equal to. So when I differentiate this, 4 times a half is 2, so it's 2t cubed. When I differentiate this, I get 3t squared. A half times 2 is 1, and so I just get a plus t. Now, I either just want to solve this equation. You could just put it straight into your calculator as a polynomial solver. If you put it straight into your calculator, you'll come up with the answers. But I'm just going to do a bit of factorising first of all. So I'm going to just take out a t. So I get 2t squared minus 3t plus 1. And I'm just going to spot the factorising that I might have here. In fact, hang on, before we did that, before I even do the factorising, I might just add something in here. And we know, because we're trying to find out when it is at rest, we know that v is equal to 0. So I'm just going to say that this is 0 equaling this. I'm just going to try and solve this equation to find out what t is. Now, if I factorise this, I actually get 2t minus 1 and t minus 1. Like I said, you could just put this equation into your calculator and it will come up with your 3 values. And your 3 values are t equals 0, t equals a half, and t equals 1. So you need to have 1, 2, 3 answers for this one to get the times when it is instantaneously at rest. And I'll go through where you get the marks for this in just a second. Now, this is only a 3-mark question, but I think it can be quite demanding in some ways. Find the total distance travelled by P in the time interval 0 to 2. Well, I'm going to do the way first of all that's a little bit longer, but I think that might relate more to some of the things we've learnt, and then I'm going to try and explain a bit more of like a common sense method afterwards that the mark scheme tries to do. So we know if you're going to try and find distance, that usually you integrate the velocity to come up with the distance that something has travelled. And the reason I'm talking about integrating the velocity here is because do you remember that if you have a curve and it goes below the axis, you have to make sure that you integrate in different sections, because if it goes below the axis, you get a negative distance. So what I'm actually going to do is I'm going to look at my velocity graph, which is my 2t cubed minus 3t squared plus t, which I've also got in factorised form, which is t, 2t minus 1 and t minus 1. I'm going to look at it and just see if it does go below the axis anywhere. So the places where it crosses is 0, a half, and 1. And it's a positive cubic, so it's going to be going like this, then it's going to be going like this, and then it's going to be coming up all the way like this. And somewhere over here is going to be 2. There's my 1, and there's my a half, and my 0. So this is fine. Between 0 and a half is fine, it's positive. However, between a half and 1, it's negative. So we're going to not be able to integrate between 0 and 2. We're going to have to integrate this as 3 separate sections. Okay, we're going to have to do section 1, section 2, and section 3. Now, let's do this. It's going to be perhaps a long way, and then I'm going to try and do the kind of easier method. Now, we're going to try and integrate the velocity, first of all, between 0, and in fact, let's not even do it between, because we're going to have to do it 3 times. Let's not even put any limits in. First of all, let's just see what happens when we integrate 2t cubed minus 3t squared plus t with respect to time. Well, we know that we're going to get t to the power of 4, increase the power and divide by the power, so it becomes a half t to the 4, and increase the power on this next bit, so it's cubed, and divide by 3, and increase the power on the next bit and divide by the reciprocal. Oh wait, it's exactly what we're expecting it to be. It's actually what x is. So we don't really need to do this each time. We can actually just think about how it's going to behave now that we have this section. So if I wanted to integrate between 0 and a half of this expression, I don't need to integrate it each time because I know that it's just going to be that same thing. I'm just going to be able to say that it is a half t to the power of 4 minus t cubed plus a half t squared, all between 0 and a half. Well, I'm going to substitute a half in here, and then I'll take away substituting in 0. But if you substitute in 0, you know the answer is going to be 0. So I'm just going to put in a half. I'm going to say a half on my calculator and store it as my answer. So I'll do a half answer to the power of 4 minus answer cubed plus a half answer squared. And we get the answer 1 over 32. You would then subtract 0, a half 0 to the power of 4 minus 0 cubed plus a half 0 squared. You just get 0 as well. Okay, so I'm now going to do it between a half and 1. And this is 2t cubed minus 3t squared plus t. And we know that this is exactly the same thing that we've got up here, except this time it's going between a half and 1. Well, let's see what happens when you substitute 1 in here. Well, 1 to the power of anything is just 1, so it's going to be a half minus 1 plus a half. That's when you substitute in 1 to all of this. And you're going to subtract what happens when you substitute in a half. Well, we already know when you substitute in a half, you get 1 over 32. Well, a half minus 1 plus a half is just 0. So it's 0 minus 1 over 32. So actually, the distance of this bit is 1 over 32. And we've worked out that the distance of this bit is also 1 over 32. We have to take the negative bit, we have to ignore that negative bit because it's below the axis, and we actually want the distance that it's travelled. This looks like a lot of work, but it isn't really. It's just a lot of writing out. So we're now going to do the last section, which is between 1 and 2, which is 2t cubed minus 3t squared plus t. And again, it's the same thing that it integrates to, and luckily it's the same as what x is. And I'm going to be doing that between 1 and 2. So I'm going to substitute 2 in here. Again, just putting 2 as the answer on my calculator. So it's going to be a half the answer to the power of 4 minus answer cubed plus a half the answer squared. And we come up with 2. And when we substitute 1 in here, do you remember what it came up with? This is what it was. It just came up with 0. So you just get 2 minus 0, which is 2. So this area of this section is just 2. So the distance travelled is 1 over 32 plus 1 over 32 plus 2. And I'm going to round that to 3 significant figures. And the answer that you get to 3 significant figures is 2.06. And it doesn't say meters or anything, so I'm just going to say 2.06 units. Now there is another way that the mark scheme thinks about this, a bit of a kind of a common sense sort of way that we have here. We have just worked out that when t is equal to 0, 1/2, and 1, the velocity is 0. So let's actually do something a bit different. Let's work out what x is in these different places. So when t equals 0, x equals 0. And actually we worked that out when we substituted in 0 in here, okay? So when t equals 0, x equals 0. When t equals 1/2, x is equal to, and I think we did that substituting in this bit. When you substituted in 1/2, we came up with 1/32. And when t is equal to 1, we got that x is equal to, do you remember when we put 1 into this bit? We actually came up with 0. And when t is equal to 2, because that's what we're also interested in at the end, when t was equal to 2, we came up with that x was 2. And you can actually check this just by substituting in 0, 1/2, 1 and 2 into x equals 1/2 t to the 4 minus t cubed plus 1/2 t squared, which was given to us in the question. That's just the expanded version of it. Now the common sense approach of this is, okay, let's draw a quick graph for a second. This is going to be a distance time graph. This is going to be the distance and the time. To start off with, at 0, it has 0 distance. Then when it gets to 1/2 a second, it's travelled up 1/32. Then when it gets to 1 second, it's travelled back to 0. Then when it gets to 2 seconds, it's travelled all the way back up to, this time quite a large number, it's travelled up to 2. And it hasn't gone below the axis at all, just because these are the only times that it's been at rest. So the total distance that it's travelled is 1/32 up, 1/32 back, and then 2 over here, 1/32, 1/32, and 2 like we have here. Kind of a strange question. I think perhaps the most familiar way would be to using this integration technique, but this is kind of what the common sense approach is that the mark scheme has used. Okay, we're nearly there. Let's have a look at just this last part now. It says, show that P will never move along the negative x-axis. Well, it's going to never move or never be along the negative x-axis. We're going to try and show that x is always greater than or equal to 0, which means it can never be negative. So I'm just going to take this bit that we've got here and see if you can remember what I said at the beginning. So we have got that. Is this part C or part D? Part C. We know that x is equal to 1/2 t squared minus 2t plus 1. And I said to you, do you think you look at this and you recognise what it might be? Hopefully you look at this and you say, I can do something to this. And you can actually factorise this. This actually factorises into this. And if you look at this, we have this multiplied by this. Well, 1/2 t squared is always going to be greater than or equal to 0 because it is being squared. And t minus 1 is always going to, t minus 1 squared is always going to be greater than or equal to 0 because it is squared. Hence, x is always going to be greater than or equal to 0, so we'll never move along the negative x-axis. Okay, only 2 marks there. Let's have a quick look at the mark scheme, if my laptop's not going to crash. Okay, so you get differentiating, multiplying out and differentiating, and you get a mark for that. You get an accuracy mark for coming up with it differentiated. You get a method mark and then an accuracy mark for solving, but really these are so easy. As soon as you've got this, you can put it straight in the calculator, come up with all 3 answers for 5 marks. So they've done their kind of common sense approach of saying, finding out what x is at all of these different times, and then saying, okay, it travels 1/32 up, 1/32 back, and then 2 back up. I personally prefer our method of integrating. I think it's a little bit clearer. And then factorising it for a method mark, and then an explanation to show that it's always going to be greater than 0 and never negative. Okay, last question now, which is question 9. This is one of my favourite types of topics. We're looking at connected particles and forces. So two small balls, P and Q, have masses 2m and km respectively, where k is less than 2. As soon as I see this, I start thinking to myself, okay, this one is lighter than 2, so I know that this one is going to be moving upwards, and this one over here is going to be accelerating downwards. The balls are attached to the end of a light string that passes over a fixed pulley. The system is held at rest, with the string taut and the hanging parts of the string vertical, as shown in figure 1. The system is released from rest, and in the subsequent motion, P moves downwards with an acceleration of magnitude 5g over 7. So I'm just going to write that the acceleration, I actually prefer writing it as 5 over 7g, but it's the same thing. And this one must have an acceleration of 5 over 7g as well. The balls are modelled as particles moving freely. The string is modelled as being light and inextensible. The pulley is modelled as being small and smooth. Using the model, find, in terms of m and g, so they're going to still be in your answer, the tension in the string. Well, let's go to our diagram and let's add on some forces. First of all, I know that this one has a mass of 2m, so it's going to have a weight of 2mg. And it feels like there is tension pulling it upwards, if you imagine being that particle. Particle Q has a mass of km, so a weight of kmg, and it feels like the tension is pulling it upwards. Now if you look at these two different scenarios that we've got here, this one I don't know T or K, so it's probably not going to be as useful to us as this one that I've got here. So I'm just going to concentrate on this one for part A of the question. Right, let's see if I can fit this in here. So for part A of the question, we want to find out the tension in the string. So we are going to resolve for particle P, and we're going to resolve downwards because that's the direction, and we're going to use an equation of motion. We're going to do F equals ma. So the resultant force for this one, well, 2mg is going down and T is going up, so it's going to be 2mg minus T. And that is equal to the mass, which is 2m, and the acceleration, which is 5 over 7g. So we then get that 2mg minus t equals, when you multiply 2 times 5/7, you get 10/7 mg. So you've got an mg and an mg, you can collect those terms together. So 2mg minus 10mg, 10 over 7 mg, sorry, is 4 over 7. So you get 4 over 7 mg is equal to, putting t on the other side, t. That's part A of the question. Now for part B of the question, it says explain why the acceleration of q also has a magnitude 5g over 7. So we need to look at these different things that we've got here and think which of these modelling assumptions tells us that q also has the same acceleration. Well, the one that it is that the string is inextensible. So we need to say here, explain why. Because the string is inextensible. That's the one modelling assumption that makes that true. Part C of the question says find the value of k. Well, if you remind ourselves, we've only looked at part of the diagram, so I'm now going to have to look at this other part of the diagram that I've got here. And we're going to do the same thing, apart from I'm going to be resolving upwards. So I'm going to resolve upwards, and I'm going to do that one for the other particle q, and I'm also going to use F equals ma. So the resultant force, it's going upwards, so we're going to do T minus kmg. So it is T minus kmg, and that is equal to its mass, which is km, multiplied by the acceleration, which is 5 over 7g. Now remember, we've just worked out what t is, so I can actually replace the t with 4 over 7 mg minus kmg equals, just writing this in a slightly different order, 5 over 7 kmg. Now you'll notice they all feature mg, so I can actually divide by mg and completely get rid of it. Let's go on to the next page. What's happening here? There we go. So I'm just going to continue this straight underneath. So I get 4 over 7 minus k equals 5 over 7k. I'm going to add k to the other side, so I get 4 over 7 equals 5 over 7k plus k. So 4 over 7 equals 5 over 7 plus 1, which is 12 over 7. I can multiply both sides by 7, so I get 4 equals 12k, divide by 12, so k equals 4 divided by 12, which is 1/3. Nearly there. Last part of the question says, identify one limitation of the model that will affect the accuracy of your answer to part C. Well, they've actually really kindly listed all of these things. So the things you could say is that the balls are modelled as particles, so we haven't taken into account air resistance. We could say the string is modelled as being light, and it might have a mass. We could say that the string is being modelled as inextensible, and it may not be inextensible. That the pulley is modelled as being smooth and it may have friction. So you can write down any of those ones. I'm just going to pick one of them. I'm going to say the pulley might not be smooth. You could write down any of those things and just say it might not be that. So let's have a quick look at the mark scheme. So the equation of motion for P, we got 2mg minus t equals 2ma, and we came up with this. So this was for trying to do the F equals ma, doing it correctly, and then coming up with t. We got the string was being modelled as inextensible. We didn't do the whole system. We look at the equation of motion for particle Q. We substituted everything in, and then after you subbed in t was 4 over 7 mg, you get another mark for that. You solve the equation, you get that k is a third. And they've gone with the model does not take into account the mass of the string, but look, there's so many you could say. The pulley may not be smooth, the pulley may not be light, particles may not be moving freely, balls may not be particles, string may not be light, string may not be inextensible, loads and loads and loads of things. So that's the end of the mechanics paper there. Let me know if you've got any questions, and I hope you did pretty well on it.